Um, okay, so uh, right. So in the first talk, I talked about reduction systems and said that this will help us describe deformations of associative algebras by basically by giving a choice of a k basis um, of the algebra, and then in this talk I'm going to explain how to use this point of view to give an explicit description of the deformed algebra, and also the conditions you have to impose in order to change the ideal or change the reduction system in a way that um, that gives actually a deformation and doesn't drop in dimension. Okay, and so underlying this this description is the theory of L-infinity algebras, which control deformation problems. And so this sort of goes back to a philosophy I think first formulated by Deligne in a letter to Goldman and Milson. And this philosophy says that in characteristic 0, any deformation problem is controlled by some DG Lie algebra. And so this means that given some deformation functor, this deformation functor is isomorphic to the deformation functor you can associate to some DG Lie algebra here. And so sort of more recently, this has become a theorem phrased in the context of the language of infinity categories. And so the theorem is by Lurie and Pridham. It says that in characteristic 0, there's an equivalence of infinity categories between the category of formal moduli problems and the infinity category of DG Lie algebras. And sort of on this side of the DG Lie algebras also sit DG Lie algebras up to homotopy. And so these are the L-infinity algebras. And yeah, then you can hope to find an L-infinity algebra or DG Lie algebra that controls your deformation problem. But this is not unique. So if you have two L-infinity quasi-isomorphic DG Lie algebras or L-infinity algebras, then the associated deformation functors are actually isomorphic. And so one famous example where this point of view was sort of used, and especially the point of view of L-infinity algebras, was that was in Conservatis's proof of his formality theorem. And so the result that he was able to prove using this is that every Poisson structure admits a deformation quantization. And so in the context of these Poisson structures and star products, there were actually two DGLAs. So here maybe G and G prime were DG Lie algebras, and on the one side the Mao-Cartan elements that were the Poisson structures, and on the other side there were sort of associative deformations of a certain type, which are star products, and then he was able to show that the deformation functors, that there's an L-infinity quasi-isomorphism between these two DG Lie algebras to show that the deformation functors are isomorphic. And then this statement follows from this. Okay. And so, yeah, just sort of the general heuristic of why these higher structures appear is that in general, if you have some algebraic structure and you try to introduce a parameter that somehow is meant to deform this algebraic structure by adding on some term. This will, in general, not satisfy the properties you would like to preserve under deformation, and so if you just add on a first order term, sometimes you have to add higher terms and to correct so sort of some correction terms. And so, for example, here if we start with associative multiplication on some associative algebra, and then we add a first order term mu1t, then we can check that this new element here defines an associative multiplication up to first order if and only if d mu1 is 1. So if it's a Hochschild cocycle. But then this term is usually or sometimes not associative at higher order. And so so the general principle is somehow that the first order deformations, you only need the information of a suitable cochain complex. And so if you try to do deformations over, say, kt over t squared, then you only need d, as we saw here. But if you try to do higher order deformations to see if you can extend this to higher orders, you will start to need more brackets. And so if you have a DG-Lie algebra that controls your deformation problem, you only need the second bracket, and then you're happy. But sometimes maybe the complex you have is nice and small, like you're going to have using the complex that comes from a reduction system, but actually you need many higher brackets to make to make it work. And so for formal deformations, you usually want a DG-Lie algebra if you can, but sometimes it's more convenient to work with an L-infinity algebra, and then you get higher brackets as well. Okay, so let me just put up the definition. So an L-infinity algebra consists of a graded vector space here with a unary bracket. So d takes one element, and then some higher brackets. And so here the degree of the higher brackets should be 2 minus n. And these are supposed to satisfy some conditions. So the first one is d squared equals 0. So that makes this into a cochain complex. And the second condition is like a Leibniz rule between the differential and the binary bracket. And then the next identity is it's like a Jacobi identity. So if this is a DG-Lie algebra, then the Jacobi identity holds, and on the right side there would be 0. But in an L-infinity algebra, there may be homotopy correction terms, and so these always involve like 2 brackets. But now we can, so on the left we have 2 binary brackets in each term, and here now we take a unary bracket and a ternary bracket in each term, and all the possible terms, and there are some signs. Okay, then there's also at higher there's the higher identities which involve the higher brackets. So these have to satisfy some additional identities. But if you've seen infinity algebras, maybe then it's it's like analogous to this. Okay, and like I said, if the higher brackets are 0 for ternary and up, then G is called a DG-Lie algebra, and then actually this here gives the Jacobi identity. Okay, and so we have higher structure on the Hochschild coaching complex, and this is the so-called Gerstenhaber bracket. And so if you have a multilinear map, F and G of that have m+1 and n+1 inputs, then you can define this this Gerstenhaber circle product F circle G by inserting the output of G. So you do G first and then insert the output into all the inputs, all the possible inputs, and then you sum over those with a sign. So there's a sign here. And then from the circle product, you can define the Gerstenhaber bracket as the commutator, graded commutator of these elements. And yeah, so sometimes people use different conventions, but here I've written m and n because this f is in degree m+1, Hochschild degree m+1. Okay, and then the theorem that Gerstenhaber proved was in the context of deformations of associative algebras. And so first thing is that this H of A, I call it, is the DG Lie algebra, where you have the shifted Hochschild complex, so you shift it by 1, so that then the shifted one F has degree, would have degree m, so this is also what appears here. And then there's the Hochschild differential D, and then the Gerstenhaber bracket, which is of degree 0 then. Okay, so this is a DG Lie algebra, and this structure actually can be used to study the deformation theory, and the reason is that a bilinear map defines an associative multiplication if and only if the Gerstenhaber bracket of mu with itself is 0. And so from the definition here, you can see that mu bracket mu is actually mu circle mu, and then plus mu circle mu again, because of the sign here, because they have both degree 1 in this case, because they take 2 inputs, and then this is a -1, so this becomes a plus here. And then mu circle mu has now a -1 here, and so this is exactly the associative multiplication defined by mu, and so this is an element in Hom A tends to 3 to A. And so if this is 0, then this is associative, because this is exactly the condition that A, B, C should equal A, B, C. Okay. Okay, so now let's look at formal one-parameter deformation. So if you have an associative algebra A, then you can try to extend or add on higher terms, possibly infinitely many higher terms, to make the formal thing an associative deformation. So by this I mean so A double brackets T as underlying vector space. So you tensor the vector space underlying A, you tensor it with KT, the formal power series, and then you use this multiplication mu T, and you want this to be associative, and then you call it a formal one-parameter deformation. And so this is associative. So then this is a deformation if and only if this term you've added on. So mu tilde, I denoted it. So this is mu 1t, and then there's a term in t squared, and so on. If and only if this satisfies this equation here. So d mu tilde plus a half mu tilde is 0. And so this just follows by sort of multiplying out the brackets. So here was associative if and only if mu t is 0. But then you can rewrite this, you can multiply this out, and then you get a term mu with mu, which is 0 because mu itself was associative. And then, then you have to observe that this bracket here, bracket with a original mu, actually defines the Hochschild differential d, and then you divide by 2 and you get this equation here. Okay, and this equation is called the Mao-Cartan equation for DG algebra. And so here we've taken the Hochschild Gerstenhaber DG algebra and tensored with this ideal. So this is the maximal ideal in the formal power series ring. So like this. And the generalization to an L-infinity algebra is that you take higher and higher brackets like this. And so in this context, the equation you have to sort of think about when this equation makes sense at all, because it's an infinite sum. But if you work with formal deformations, then this infinite sum converges in the t-adic topology. So at each power of t, there's only finitely many terms, because whenever you have single x, you get a power of, you get at least a single power of t. Okay. Yeah, just to point out again, so if you only do first order deformations, then this Mao-Cartan equation actually reads d mu1 equals 0. So mu1 should be a Hochschild 2 cycle. And then there's also the notion of equivalence of deformations. And so you say two first order deformations are equivalent if there exists a map phi here, which is of the following form. So it looks like identity plus phi1 of t, and phi1 is an element from A to A, such that if you take the associative, the first order deformation associated to mu1 tilde, you call it star tilde, and the one to mu1 you call star. Then you can send them. So you use phi on A, and then you use the 1 multiplication, and then you undo phi by using phi inverse. And if you then get the other multiplication, then you say the equivalent. It turns out that that this equivalence is given exactly by co-boundaries. So in this sense, the second Hochschild cohomology sort of controls the deformations of associative algebras, because the first order term is a 2 co-cycle, and they're equivalent up to 2 co-boundaries. Okay. And so now I will go back to the resolution that I talked about in the first talk. And so if you have an associative algebra A, which you've written as KQ mod I, where Q is some quiver with relations, and you have a reduction system satisfying the diamond condition for this ideal, then we get this this resolution from Chohi and Solotar P, and then there's a retract. There's a retract between P and the Hochschild cochain, or the Hochschild cochain complex, or the reduced normalized Hochschild cochain complex. And then we can use the construction used in the homotopy transfer theorem to transfer the higher structure that's on this complex here, and this can be transferred to the smaller complex. And what you get is the structure of an L infinity algebra. And so we call this PQR. And as underlying cochain complex, it has this cochain complex coming from the Chohi-Solotar resolution. And then it has an infinite number of higher brackets. And so these brackets can be defined using the comparison maps here of the between these two cochain complex and also the homotopy H. And so if you have n elements G1 up to Gn, then you can define their bracket as a sum over trees. And so at each leaf, you put one of the GIs, and then you use the comparison morphism to send these over from P to C, and then you put them at the leaves of the tree, and then you use the bracket, and then you use the homotopy H, and you do this again and again. And after using the last bracket, you use F again to go back. So use F again to go back to the complex, and then this defines an L infinity algebra with these brackets. Okay, and the statement also gives that this G upper dot here actually extends to an L infinity quasi-isomorphism between this new L infinity algebra structure on this complex P and the Hochschild-Gerstenhaber DG Lie algebra. Okay, and then by the general theory of deformation theory via L infinity or DG Lie algebras, you get that on the right you have this deformation functor which controls deformations of the associative algebra structure on A, and this deformation functor is actually isomorphic to the one that you can define from this L infinity algebra. And and on the left hand side, one can check that actually this controls sort of deformations of the reduction system. So if you try to interpret what this means, what the Mao-Cartan element there is, then it looks like what should be a formal deformation of the reduction system. Okay, so how is this deformation functor defined then? So given any L infinity algebra or DG Lie algebra G, you take a certain functor here, MCG, and then you quotient out by homotopy or gauge equivalence. And so MCG is this functor that takes a local complete Noetherian K algebra or maybe Artinian algebra. So B with some maximal ideal M, and it sends this to the set of Marquardt elements. So that means the elements which live in G1 tensor M, and that satisfy the Marquardt equation. Okay, so for example, here X we said could be something like mu1t plus mu2t squared and so on. And yes, and the homotopy equivalence of Marquardt elements can be defined as follows. So you have somehow your tensor first with something like simplicial differential forms on the unit interval. And yeah, actually, this is a commutative DG algebra with one parameter, which I've called t. Maybe this was not a good idea, because this should be, yeah, we call this tau, d tau, because t was already the parameter of the deformation. Okay, and you want to look at the Marquardt elements of this bigger, this new L infinity algebra, and such that when you evaluate tau at 0 and at 1, you get two different Marquardt elements of the original algebra G. Okay. Right, and so now we have this this structure that maybe looks at first sight maybe looks a bit complicated, because you have these infinitely many brackets, and L infinity algebra sort of looks scary, but actually it turns out that there's a nice nice sort of hands-on way to compute Marquardt, or to check the Marquardt equation for this L infinity algebra. And so this is what I'm going to explain next, and then soon we will see an example, and hopefully then, at least by then, yeah, it becomes more clear that this is something very practical. Okay, so the idea is that given quotient of a path algebra with a reduction system R satisfying the diamond condition for the ideal, we can actually view these second entries here, Fs. We can view them as coming from a KQ0 bimodule map F. So that goes from Ks to A to the algebra. And so here we said this isomorphism sort of comes from the diamond lemma, from this diamond condition. And these you can view as elements in KQ. Okay, and so then you can sort of set Fs to be sigma of f of s. So f is now this function, and it sends an element in S to the algebra A, and then you can use the section A to KQ, which is a section of the projection. And so the original reduction system looks like this, and now you can try to deform it to this, where you add on this extra term GS. And so G is also, like F itself, is also an element here. Okay. And yes, and in order to describe this criterion for checking whether an element satisfies the Markov equation for this L infinity algebra, let me define this following bilinear operation. So let G be an element here, and now we work in the formal setting where we tensor with the maximal ideal. So this could be just tensor with T, so that T, so that, for example, G could look like G1 T plus G2 T squared and so on. And yes, and then this bilinear operation star G is defined as follows. You take the old product and then you take a sum over star G Ks with B. And the idea here is that this captures precisely the reductions using RG instead of R, where RG was, if I go back, RG was this this sort of modified reduction system here. Okay, and so more precisely, we say this A star GKB is the sum of all the terms you obtain by performing rightmost reductions on sigma A, sigma B. So you can take two elements in A, you lift them to the path algebra KQ, and then you just concatenate them, and then you use reductions over and over again. And but now you use reductions inside the new reduction system, so RG. And then at each step, you sort of have get a sum, and you can, so you can start with a path P, for example, and then performing one reduction means you use F or G. You replace S here either by Fs or by Gs, and then you take the sum. And so you get a diagram like this, where you can either use this reduction, the old reduction again and again, or you can use these reductions using G. Okay, and then you get sort of a infinite expression like this. But if you sort of stay on the left and always use F, then you know this process will stop, because the old reduction system was reduction finite and reduction unique. And then you can use like G once and then just keep using Fs, or you can use G maybe at the beginning many times. And this process will stop at each finite power of T. You only get finitely many terms. And so this will probably become clearer in the example, which is about to come up after this slide. So let me just say the statement first, which is if you have such an element in Hom Ks to A, tensor M, so G is an element like this, then this G satisfies the Markov equation of this L infinity algebra PQR tensor M. If and only if for every element in S3, and so I should remind you what this was. So these were the overlaps. And so it looked like if you have a path, and then maybe an element in S here as a subpath, and then another element in S as a subpath. So for each overlap, you could you have the following conditions. So W1 star G, so associativity of this new bilinear operation that we call star G. And so in this case here, so this would be like W1, and then and this overlap here is W2, and then this last bit here would be W3. Okay. And right, and something similar also holds in the non-formal case if you require that this star GK is 0 for K large enough. And so if this expression makes sense at all, then it gives you a Maurer-Cartan element, and it always makes sense in the formal context. Okay, and yes, in this case, the star G actually also defines an associative multiplication on either on the old vector space A, or if you tensor by a formal power series ring, for example, then this is also associative on this formal power series ring. Okay, and yeah, and so this star G operation is actually essentially what you get by using the higher terms in the comparison morphism, where this is yeah, this is sort of part of the L infinity quasi-isomorphism between the algebra PQR and H of A. Okay. Yes, and so for the rest of the talk, I will just go through one explicit example, which I think shows well how you can use this point of view to compute examples and compute deformations whenever you have written an algebra as the path algebra of a quiver with relations. Okay, so this example is an example of a Brauer tree algebra, and there's a paper by Mazurczuk and Stroppe, and they found that the regular blocks of so-called finitely generated cuspidal weight SLN modules are equivalent to the category of finite-dimensional modules over a deformation of this algebra. So the deformation here sort of naturally appears, and then you can ask, or maybe you want to know what this deformation looks like. And so, yeah, so this Brauer tree algebra has a number of vertices, and arrows between these, always 2 cycles between them, and then yeah, you have these relations. Like if you go right twice, this is 0. If you go left twice, this is also 0. And if you do a loop on the right, then this is the same as doing a loop on the left. Okay, so let me describe the deformations of the sort of small dimensional case. And so I just take 3 vertices and the 4 arrows that you can see. And yes, and in order to describe the deformation theory, we said we should work with a reduction system. And so the reduction system here, we can try to guess from the ideal. So the first guess would be just to choose the relations here. A1, A2 should map to 0. So this was one of the relations. B2, B1 was the other relation. And then we had a relation here, A2, B2, minus B1A1. And then we say, okay, maybe we want to reduce this one here to this one. And so we write this in the first entry and this, the other term in the second entry. And we all almost get what we want. So we see that our tilde is reduction finite. That's good. The ideal it generates, or the differences of the entries, ideal generates the ideal we're looking for, but it's actually not reduction unique. And so there are two overlaps. So the diamond lemma told us that reduction uniqueness, you only have to check reduction uniqueness on the overlaps. And so here we have an overlap between A2 here overlaps with A2 here. And so we have this overlap of A1, A2, B2. And if we replace A1, A2 by 0 in the reduction system, we get 0. And on the right-hand side, we get A1, B1, A1. And this is not yet 0. And similarly, on the other side, we get A2, B2, B1. This is an overlap. Yeah, on the one side we get 0, and on the other side we get B1, A1, B1. And so then we add these to the reduction system. And then we can check this now satisfies the diamond condition, because it resolved the old overlaps, and the new overlaps that have appeared are the following. So like A1, B1, A1, A2. And on both sides, they always resolve to 0. So this is now a reduction system that's reduction unique, and it still generates the same ideal. Okay, so now we have our reduction system, and then we can look at this set S of first entries. And this has now 5 elements. And right, and now the diamond lemma gives us an explicit k-basis of the algebra, right? So we have 3 idempotents at the vertices, E1, E2, E3. We have the 4 arrows, the 2 A's and 2 B's, and then we have 3 irreducible paths of length 2. And the other path of length 2 that doesn't appear there is A2, B2, right? Because this gets reduced to B1, A1. Okay, and so we get 10 elements, so the algebra is 10-dimensional. And now we had 5 elements in S. So when we look at an element G in Hom KS to A, bimodule morphism, we now should look at, yeah, so we want to send it to A. So we look at parallel irreducible paths. And so A1, B1, A1 here, right? It does this, it goes A1, B1, then A1 again. And so this is the only path that's parallel to this, which is also irreducible, is A1. So now we can send it to some multiple of A1. And similarly for B1, A1, B1, can send it to multiple of B1. And here actually there are no paths which are irreducible and parallel to A1, A2. And here we have again 2 parallel paths. One is so this is the loop that does this between these 2 vertices. And so either we can stay at the left vertex, or we can do this. So these are E2 and B1, A1. Right. And so we have four possible paths here. So we have four coefficients. And so as a k-vector space, this Hom k is to A is four-dimensional with these coordinates. And so here you can see that that if you try to sort of use this approach by looking at all bilinear maps from A to A and then figuring out which of those are maybe associative, then you would have to look at Hom A tensor A to A, which is 1000-dimensional in this case. So it's tensor over K. Okay, and yeah, here we just have to look at something sort of four-dimensional. Okay, and now we would like to determine conditions on these four coefficients to define a deformation of A, and we can use the criterion. Right, and the criterion says that it should satisfy associativity on the overlaps. And so here in this set S, we have overlaps that I've marked here, and so there are 6 overlaps, and so we should check 6 equations, and yeah, and just you can look at the first equation, and so A1 B1 star A1. So there was an overlap here. So this is an element in S, they overlap in A1. And so the A1 sort of sits here on this side and on this side in the middle. And right, and now we would like to compute this star G. And what do? We use the two paths here, A1, B1 and A1 to calculate this here. We write them next to each other, and then for star G0, we don't use G at all, we just use the old reduction. And so on A1, B1, A1, this was just sent to 0, the old reduction system. So maybe I can show this again here. So A1, B1, A1, sent to 0. Okay, and now we can also use G. And so this is the next term here, A1, B1, star G1 with A1 which means we use G once. And now we said if we use G once, then we should send A1, B1, A1 to lambda times A1. And so this is this term here. And you can check that star G2 is 0 and the higher ones as well. Okay, and now we've sort of calculated the first bracket here, and the result is just this, lambda times A1. And so now we calculated the second star, so lambda 1 A1 star star G with A2 is we don't use G at all, means we just use the old relation on A1, A2, that was 0. But also the new relation with G, this is also 0 here. So actually this now also becomes 0, because the definition of G, we said there's no parallel path, no path which is irreducible and parallel to A1, A2, so cannot deform it. And then on the right-hand side, we also get this A1 star A2. This also gives 0. Okay, and then there's a second a second example, which if you go through it carefully, then then you will find that this time you actually get a condition. So maybe let's do this quickly. So again, we don't use G means for, so on the left-hand side we have 0 because we just calculated A1 star A2, so this is 0. But on the right-hand side, we now should first calculate A2, B2. So when we don't use G, just use the old relation, and which sends A to B2 to B1, A1. Okay, we can also use G once, and then we get this term here. And when we've used G once, then we find it's already irreducible, and then we just get this term here. And so we have two terms in star G because star G was sort of the sum over the ones star GK, right? So we should sum these. So there's two terms we now need to compute. Just the first one with A1, so this A1 here. And so the first equation gives this condition, lambda A1, and the second term here, when you start by A1 from the left, you get these terms. So then you collect them all together. So I've marked them sort of in red here. And the left-hand side was 0, so this is the condition that's imposed by this second equation. So we get the condition that mu plus lambda into 1 plus mu prime should be 0. And like this one also gets one further condition, and that is that lambda should equal lambda prime. Okay, and so this is sort of the end of the computation of the Marot-Cartan, of the equations imposed by the Marot-Cartan equation. And now we should maybe make sense of this. And and we so one thing we can do is we just view lambda and mu as constants, and then we get a two-dimensional family because mu is sort of determined by lambda and mu prime, and lambda prime is also determined by lambda, so sort of get a nice family of algebras if we choose lambda and mu prime freely. But if we want to do this in the formal context, we can also talk about equivalence of Marot-Cartan elements, and then lambda should actually be viewed as an element in this ideal T. And so lambda is like a formal power series maybe. And then you can find that for general power series now, lambda and mu prime, we can kill mu prime like this. So a general Marot-Cartan element here is actually equivalent to this Marot-Cartan element. And here we just need the first order term of lambda. And so this is the condition we get from the Marot-Cartan equation. And then this mu prime, which was also a free choice, we can kill this. Okay, and so what we get is that we have a formal deformation, which is sort of one-dimensional. In fact, it also admits an algebraization because the star product is defined is not a formal product anymore if you just have T here. And so it's defined also if we just tensor by KT, polynomial ring in one variable. And we get a one-dimensional family of 10-dimensional algebras, and these are the deformations of this Brauer tree algebra. Yeah. And so the computation I've done here for A3, but if you just replace like 1 and 2 by I and I plus 1, then this is exactly the same computation. And so, yeah, so in this way you get the deformations of A n minus 1. Okay, so let me, in the last 2 minutes, let me just summarize. Oh yeah, maybe I can say this again, that the star G is now an explicit expression, which you can write down as some sort of multiplication table if you like. So here, I mean, like B2 star E1 is 0. And then, so these gray entries were the old multiplications, and now you've changed them here in these spots. It's not 0 anymore. Right, and so for lambda equals 0, you get the old Brauer tree algebra, and for lambda some constant, you get a deformation of it. Okay, and so I'll just end with a short summary of what happened. So if you're given an algebra A, which is path algebra of a quiver with relations, you can compute a reduction system R satisfying the diamond condition. And if the computation, maybe it's more convenient, if somebody has computed a non-commutative Gröbner basis, you can just use this. And then once you have a reduction system, you get this Chohi-Solotar resolution, which is a much smaller resolution than the bar resolution, and then you can take study deformations of A, associative deformations of A, just in terms of deformations of the reduction system. And the way you can do this is to look at the Mao-Cartan equation for the L infinity algebra structure on this complex P that we get by homotopy transfer. And to check this, you just sort of follow some combinatorial rule, which is checking associativity of this new star product on the overlaps. Okay, and once you've checked that this is true, then this actually gives the very same formula gives an associative product on all of the formal deformation or of the original algebra. And this is then, the deformation. Okay, I will stop here.
Thank you.